and energy. Work. Introduction. In our daily life, we use the word work many times. Generally, any mental or physical activity is referred to as work. Thus, according to it, we can say that the work is being performed in all the four activities shown over here. But if we observe these activities from scientific point of view, work is not said to be done in all the four activities. Work has a special meaning in physics. Work is said to be done when a force applied on an object causes displacement of the object. Thus, from scientific point of view, we can rightly say that the work is not done by Tanvi, who is studying, and Sana, who is watching television. But work is done by Vaibhav, who is playing with the ball, and by Ramu, who is carrying the wooden log. When we walk or run, the energy in our body is used to do the necessary work. Here, physical work is done. On the other hand, when we study, mental work is done. In physics, we deal with physical work. Come, after understanding the meaning of word work in context of everyday life and physics, let us now proceed further. We have already learnt that the work done by a force acting on an object is the product of the magnitude of the force and the displacement of the object in the direction of the force. We have also learnt about the different types of forces in previous grade. Remember, muscular force, gravitational force, magnetic force, electrostatic force, and frictional force are the different types of forces. Come, let us now study an example and identify the different types of forces applied in the example. Meenakshi wants to displace a wooden block from point A to point B along the surface of a table. To do so, she applied force F. Can you identify which type of force did Meenakshi apply to perform this task? Right, she used the muscular force to perform this work. While applying force F out of all the energy spent by Meenakshi, some amount of energy is used to produce acceleration in the wooden block. Now, can you tell the remaining amount of energy is utilized to overcome which type of force? What do you think? Yes, absolutely right. The remaining amount of energy is utilized to overcome the frictional force. Come, after this quick revision about the concept of work and force, let us study about work in more detail. More about work. We have already learned how to calculate the work done on an object when the displacement is in the direction of the applied force. But if the displacement of the object is not in the direction of the applied force, then let us understand how to calculate the amount of work done. Two events are taking place over here. In the first event, Meera is pulling a toy car with the help of a string. In the second event, a large vehicle is towing a small car. What do you think? Are the directions of force applied and displacement of vehicles the same or different? Absolutely right. In both the cases, the directions of force and displacement are different. The direction of force makes an angle with the direction of displacement. Let us see how to calculate work done in such cases. For this, let us consider the first case. When Meera pulls the toy car, force is applied along the direction of the string, while the car is pulled along the horizontal, that is, the toy car is displaced in the horizontal direction on the ground. In this case, in order to calculate the amount of work done, we have to convert the applied force into the force acting along the direction of displacement. In this example, let F be the applied force and F1 be its component in the direction of displacement. Let S be the displacement. Thus, the amount of work done, W, is equal to force acting along the direction of displacement, F1, into displacement, S. Equation 1. The force F is applied in the direction of the string, that is, at an angle with the horizontal. Let theta be the angle that the string makes with the horizontal. To find out the component of F in the direction of displacement, that is F1, let us draw a perpendicular from F to F1. Now, from the right-angled triangle so formed, let us determine the component F1 of the applied force F, which acts in the horizontal direction by means of trigonometry. Cos theta is equal to base upon hypotenuse, which is equal to F1 upon F. Therefore, F1 is equal to F into cos theta. Substituting the value of F1 in equation 1, we get work W is equal to F into cos theta into S. Thus, the work done W is equal to F into S into cos theta. Come, let us now find out the work done for the specific values of theta and enter the conclusions in a table. Suppose the value of theta is 0 degree, that is, the angle between the force and displacement is 0 degree. When theta is 0 degree, the value of cos theta is 1. We have learnt that the work W is equal to force F into displacement S into cos theta, which is equal to F into S into 1, which is equal to F into S. Here, the value of work done is positive. Thus, the work done by the force is positive. Suppose the value of theta is 90 degree. That is, the angle between the force and displacement is 90 degree. When theta is 90 degree, the value of cos theta is 0. Work done W is equal to force F into displacement S into cos theta, which is equal to F into S into 0, which is equal to 0. Here, the value of work done is 0. Thus, the work done by the force is 0. Suppose the value of theta is 180 degree, that is, the angle between the force and displacement is 180 degree. When theta is 180 degree, the value of cos theta is minus 1. Work done W is equal to force F into displacement S into cos theta, which is equal to F into S into minus 1, which is equal to minus F into S. Here, the value of work done is negative. Thus, the work done by the force is negative. After calculating the work done for the specific values of theta, we come to know that when the force and the displacement have the same direction, that is, when the value of theta is 0 degree, the work done by the force is maximum. On the other hand, when the force and the displacement have opposite directions, that is, when the value of theta is 180 degree, the work done by the force is minimum. Come, let us now learn about the unit of work. Unit of work. Work is equal to force into displacement. In SI system, the unit of force is Newton and the unit of displacement is meter. Thus, the unit of work is Newton meter. This is called joule. If a force of 1 Newton displaces an object through 1 meter in the direction of the force, the amount of work done on the object is 1 joule. Therefore, 1 joule, J, is equal to 1 Newton N into 1 meter M. In CGS system, the unit of force is dyne and that of displacement is centimeter. Thus, the unit of work done is dyne centimeter. This is called an erg. If a force of 1 dyne displaces an object through 1 centimeter in the direction of the force, the amount of work done is 1 erg. Therefore, 1 erg is equal to 1 dyne into 1 centimeter. Come, let us now study about the relationship between joule and erg. We know that 1 Newton is equal to 10 raised to 5 dyne and 1 meter is equal to 10 raised to 2 centimeter. Work is equal to force into displacement. 1 joule is equal to 1 Newton into 1 meter, which is equal to 10 raised to 5 dyne into 10 raised to 2 centimeter, which is equal to 10 raised to 7 dyne centimeter. Therefore, 1 joule is equal to 10 raised to 7 erg. Come, after studying about the unit of work, let us now learn about positive, negative, and zero work. Positive, negative, and zero work. Come, let us discuss about the directions of force and of displacement in each of these cases. In the first case, 3 people are pushing a stalled auto rickshaw, due to which the rickshaw is getting gradually displaced in the direction of force. In the next case, Shashank is catching the ball which his friend has thrown towards him. Here, the force applied by Shashank and the displacement of the ball are in opposite directions. In the next case, Bilal is trying to push the wall with all his strength. Here, he is applying force on the wall, but no displacement of the wall is observed. In the next case, Rajas has tied a stone to one end of a string and is swinging it round and round by the other end of the string. At each point of the circular path taken by the stone, the displacement and the applied force are perpendicular to each other. In the next case, Vishal is walking up the staircase. Here, the applied force and the displacement are in the same direction. In the next case, a squirrel is climbing a tree. Here also, the applied force and the displacement are in the same direction. In the next case, the moving vehicle is stopped by applying brakes. In this case, the force applied by the brakes and the displacement of the vehicle are in opposite directions. After observing the directions of force and displacement in each of these examples, we notice that in some examples, the direction of the force and that of displacement is the same. In some other cases, the direction of force and that of displacement is opposite to each other, while in some cases, the directions of both force and displacement are perpendicular to each other. When the force and the displacement are in the same direction, that is, when theta is 0 degree, the work done by the force is positive. When the force and the displacement are in opposite directions, that is, when theta is 180 degree, the work done by the force is negative. When the applied force does not cause any displacement, or when the force and the displacement are perpendicular to each other, that is, when theta is 90 degree, the work done by the force is 0. Come, let us now perform an activity. Activity. First, take a plastic cup and make a hole in the center of its bottom with the help of a thick needle. Now, take a long thread, double it and pass it through the hole. Tie a thick enough knot at the end so that the knot will not pass through the hole, taking care that the 2 loose ends are below the bottom of the cup. Now, let us tie a nut each to the 2 ends of the thread. Put this cup on a table. Keep one of the nuts in the cup and let the thread carrying the other nut hang down along the side of the table. We observe that the cup gets pulled. Can you tell why does this happen? The force applied by the thread and the nut on the cup is more than the force of the friction between cup and table and thread. Therefore, the cup gets pulled in this direction. Can you tell which type of work is performed over here? Yes, the work performed over here is positive work. Come, let us now proceed to the next part of the activity. Place the cup at its original position. When the cup is sliding along the table, stop it by putting a ruler in its path. Can you tell what is the relation between the displacement of the cup and the force applied through the ruler? Absolutely right. The direction of displacement of the cup and the direction of the force applied through the ruler is perpendicular to each other. The work performed over here is zero work. Now, let us once again place the cup at its original position. But this time, leave the two nuts hanging on opposite sides of the table. What do we observe? We observe that this time the cup doesn't get displaced. This happens because the force acting on the cup is zero. The two forces that are acting on the cup are balanced. Therefore, the cup doesn't get displaced. The work done by the force in this case is zero. Thus, from this activity, we understand that an object gets displaced due to action of unbalanced force. Come, after learning about positive, negative, and zero work in detail, let us now study a small example. Suppose an artificial satellite is moving around the Earth in a circular orbit. Then, can you tell what would be the work done by the gravitational force acting on the satellite? The gravitational force acting on the satellite, which is along the radius of the circle, and its displacement, which is along the tangent to the circle, are both perpendicular to each other. Thus, the work done by the gravitational force is zero. Institutes at work. The National Physical Laboratory, New Delhi, was conceptualized in 1943. It functions under the Council of Scientific and Industrial Research. It conducts basic research in the various branches of physics and helps various industries and institutes engaged in developmental work. Its main objective is to establish national standards of various physical quantities. Come, let us now solve some examples. Solved examples. 1. Calculate the work done to take an object of mass 20 kilograms to a height of 10 meters. Solution. Let us first note down the given things. Mass m is equal to 20 kilograms. Displacement s is equal to 10 meters. Acceleration due to gravity g is equal to 9.8 meter per second square. First, we will calculate the force. Force F is equal to mass m into acceleration due to gravity g, which is equal to 20 into minus 9.8. The negative sign is taken over here because the displacement is opposite to the direction of the force. Thus, force applied is equal to minus 196 Newton. Now, we will calculate the work done. Work W is equal to force F into displacement S, which is equal to minus 196 into 10. That is, minus 1960 joules. The negative sign appears because the direction of force is opposite to the direction of displacement, so that the work done is negative. 2. Praveen has applied a force of 100 Newton on an object at an angle of 60 degree to the horizontal. The object gets displaced in the horizontal direction and 400 joules work is done. What is the displacement of the object? Solution. Let us first note down the given things. Angle between the force applied and displacement, theta, is equal to 60 degree. Force F is equal to 100 Newton. Work W is equal to 400 joules. Work W is equal to force F into displacement S into cos theta. 400 is equal to 100 into S into 1 upon 2. 400 upon 100 is equal to S into 1 upon 2. 4 into 2 is equal to S. Therefore, S is equal to 8 meters. The object will be displaced through 8 meters. Come, let us now proceed further.